All right, you people. Okay, hello?
Hello.
Hello? All right, so listen. All right, for you guys today, especially those people that are not here right now, okay, that are not here in class right now, certain people. All right, so we're going to go over, and we have a guest instructor today. All right? So we have Coach Grill today. He's going to grill you on the BC topics here. So starting on example 6, 7.7, go ahead, just project your voice. That's all you got to do.
Alrighty. So, first thing I do when I look at this integral is I see, well, if we're trying to determine whether this converges or diverges, which one of my bounds might be a problem? My 0 or my pi over 2?
Pi over 2. Because then sine over, yeah. Then it would be undefined.
Because then it would be undefined, right? So it approaches, like it just kind of veers off because it's undefined there. So to determine whether it converges or diverges, I could change this to the limit as x approaches pi over 2 and just see, well, since we can't actually get to pi over 2, we can kind of get to around pi over 2 and just see what's happening as I take the limit of that. So I will take the limit as x approaches pi over 2 from 0 to x of tan x dx. So this is to check if we have a convergent or divergent integral. Well, I can evaluate my tan x, and to evaluate my tan x, I can do like a little bit of u sub, but hopefully I can navigate around that and just do that a little bit quicker. Does anybody know the antiderivative of tangent of x? If you do, cool. If not, that's okay. We can go through the whole like legwork right now.
Well, we should, but we didn't memorize it.
I don't even think I have it memorized, but I believe it's like the natural log of cosine of x, or x times the natural log of cosine of x. I can go through the u substitution real quick if you guys do not know it. So as you guys do know, tangent of x is going to be sine x over cosine of x. If I were to do a u sub, I could say, let's let u equal my sine or my cosine of x. Which one is like the more tantalizing substitution here? You bet it's sine of x, because that has a derivative of cosine, and I can sub in my u directly and things are good. So I can say, let's let u equal sine of x, so du equals cosine x dx. U equals sine, du equals cosine. Wait a second, you guys screwed me up because I don't want my du in the denominator. I want my u in the denominator because that gives me a nice natural log. Uh-oh. So u is going to equal cosine of x, so du is going to equal negative sine x dx. And I can divide over that negative 1 just so I have that attached to my du. And I can see that my tangent of x, when I throw a u sub in for it, is going to be equal to negative 1 over u du. So, got kind of a lot of stuff going on right here. We can take the antiderivative of this because this does have an easy elementary antiderivative. Just if I have 1 over u, and I promise you that's a u, if I take the antiderivative of 1 over u, I get what?
Natural log of
Negative.
Thank you. We get a negative natural log of u. So I have a negative ln of the absolute value of u, which I can re-sub back in my cosine of x. So I have, this is equal to, I'm running out of space. This is equal to the limit as x approaches pi over 2 of the negative natural log of the absolute value of cosine of x, and we still have to evaluate this limit. We still have to evaluate this integral. So we're evaluating from 0 to cosine, from 0 to x for my cosine of x. And then when I plug in my bounds, I can finally take that limit, and guess what? We're back in Calc 1. We're back in familiar territory for me, and I can take a limit. I hope you guys can too. So just take a moment. I'm gonna pause right here. Take a moment. Go ahead, plug your bounds in, and compute that limit for me to see if we have a convergent or a divergent integral. Wow, that is chicken scratch right there.
In total, like at the end.
I promise you, it's like slightly more neat if it's on my board. Not much, but it's like slightly.
No, because I'm sorry, I keep thinking it's just
So I'm hearing converges, I'm hearing diverges. Let's take a quick look at our criteria for convergent and divergent integrals. If our integral were to converge, what kind of value would I be left with after I evaluated this?
Like convergent?
It feels to be convergent.
An actual real number?
Yeah.
Some kind of real number. Like we want something to be well defined if it's going to be convergent. If it's to be divergent, what are we looking for?
Undefined, an idea.
We're looking for some kind of positive infinity, some kind of negative infinity, or some kind of does not exist. Well, when we evaluated this, did we get that far, by the way? Did we get that far? Did we evaluate our integral?
Yeah.
Okay, so when we evaluate our integral, are we saying it's convergent or divergent?
When ln of
Is ln the natural log of 0 defined?
Yeah, so
No.
then it'll be divergent.
not, because wouldn't it only be a 1
Right.
so anything about it going to be divergent because this doesn't exist.
So it is a divergent integral, and I don't know, does he have another slide that I can go to, like, to write on a separate sheet? Or do I have to, like, erase some of this?
Up top,
Can I go right here? Or can I go insert?
Yeah.
Insert new page.
Insert.
Page. Blank page after current. Fantastic. Okay. So just to rewrite this, we're going to check and see that this is going to be a divergent integral. The limit as x approaches pi over 2 for the integral from 0 to pi over 2 of the negative natural log of the absolute value of cos x. So, sorry, this is an x, not a pi over 2. I go ahead, I evaluate my upper bound, so I have the negative natural log of the absolute value of x minus, but minus plus, plus the natural log of 0. And this whole thing, we're taking the limit as x approaches pi over 2. Well, if x approaches pi over 2, more or less we could just say, let's substitute this pi over 2 in for this natural log of x. Cool. Cool beans, that's fine. No problem with doing that. This is good. Like, I could just almost give that a thumbs up and just say, let's move on. However, I still have this numerical value that I have to evaluate. And if we think about what value the natural log of 0 approaches, where are we headed to? It's positive or negative infinity?
Wait, is it cosine of 0?
Yeah,
or
just
just
negative.
0?
ln of cosine of 0. Sorry. That is definitely my fault. Because the natural log of cosine of 0 is just going to be the natural log of 1.
Yeah.
That's my fault.
You're okay.
Okay. So we can add together these two natural logs, and there's a beautiful natural log property that says I can have the products of their inputs. So I can really just evaluate the natural log, bear with me, the natural log of, since this is a negative sign, I could have a x to the negative 1 power. I can multiply my x and my 1 together, and this is just the natural log of 1 over x as x approaches pi over 2. My bad, we're actually good. My bad, this actually converges. My bad, I saw the natural log of 0 and I wanted to jump at it so much and say it was a divergent integral. I fell for the bait.
Wait, so isn't it natural log of cosine of x?
Yeah,
Shouldn't
not
it be
just
natural
x.
log of cosine of pi halves?
Yeah. And then that
Gee,
would-
wait,
yeah.
wait,
No, no, no.
wait.
See,
But
wouldn't it
then-
be cosine x, and then when you plug in, it would be cosine of pi halves, which would then be 0, so then you do have an element 0. That's what we.
That's-
There we go.
That's what
Hey,
we
I'm
got.
making a ton of mistakes right now. So,
You know what?
the natural log
Intentionally.
of cosine of x somehow disappeared. We have the natural log of x. We should have put in a natural log of cosine of x. We should have put in a natural log of cosine of x. We should have then evaluated what cosine was rather than what the natural log was, and then evaluated the natural log because we had that composite function there. So, to then backtrack and say, I don't even know if I'm helping right now, but to backtrack and say that, let's go erase this. Is there a better way to do this?
I think you started.
You can circle it like a
Then
smart
tap
Tell
board.
them tap the middle.
No.
Maybe not.
That's
Maybe
like
not
Violet's
that.
board. Violet's board.
Maybe get a
Well,
bigger
that's
eraser.
I know the smart board does it, but
Yeah.
I don't think
I mean, you
the
can make the erase. This is like a
Promethean app does it.
Different boards?
Yeah, Pacho's board isn't a smart board. It's a manageable board.
Yeah, it's calibrated and everything.
So let's just backtrack real quick. We're gonna plug in and evaluate our balance as the negative natural log of the absolute value of cosine of x. My apologies. The negative natural log of cosine of x. Cosine of x minus plus the natural log of cosine of 0. Alright, fantastic. I can evaluate my numerical bound, cosine of 0. Where are we at? 1. Cosine of 0, we just got a 1. So the natural log of 1, I'll just put the absolute value of 1 just to kind of keep with that notation, but the natural log of 1, no problem so far. Now I need to evaluate my limit because x is approaching pi over 2, and cosine of pi over 2, that's going to give me what? 0. So that's that problem that we were talking about before. We mentioned it, or I mentioned it, but I mentioned it in the wrong way. I jumped at that natural log of 0. However, now I see the natural log of 0. That's the kink in my hose. That definitely tells me that the natural log of 0 approaches what value?
in like down negative.
Positive or negative infinity?
Negative.
Negative infinity.
Negative infinity. Okay, so we can say that the natural log of 1, that's 0. We're good. But the natural log of 0, this is some negative infinity. Therefore, we're going to be divergent. So the criteria for divergence, we're looking for positive infinities, negative infinities, or D and E's does not exist when we actually evaluate some kind of limit. What's the next problem?
The last one? No.
There's more. Oh, hey. So, guess what? We have the same kind of linearity properties that we've been dealing with integrals. However, in the context of an improper integral, it may sometimes help to break it up into two separate bounds. Okay, this is akin to me adding one area together with another area and then just pasting it back together. However, with an improper integral, I can figure out, let's just isolate the bad part. Like this huge wall of text, I don't even have to look at it. Let's just isolate the bad part in that we can get whatever evaluates to be a numerical value, and then whatever evaluates to be something that's bad is just like, let's put it over here. We're going to put it in timeout. We're going to say, I know what you did. So to evaluate a divergent integral, sometimes you might want to split your bounds of your integrand to be two separate things. So if you need to write that down, or
They have it on
summarize
their
that.
notes.
Oh,
They
okay.
have the PowerPoints of this.
I have a quick question.
Yes.
Kind of about the last one, or in general. So if it's approaching 0, would that still be that would still be convergent, right? 'Cause it's
Converging. 0 is a number. If it's going to infinity or negative infinity, that is not a number. Remember, infinity is an idea, not a number. You cannot put it on a number level.
If you had a 1 over 0, however, that's a problem. Some things when you plug in 0 are a problem, but the number 0 itself is. Okay, so we're going to determine whether this rational boy right here converges or diverges. I feel like since we went through the very last kind of theorem, let's see, before I even go through with evaluating this, how may I want to apply this idea to this integral? I'm hearing we want to break our integrand up into 0 to 1, 1 to 2, okay? I want to break it up to two separate integrals because our problem occurs when x equals what? 1. We're going to have something that's undefined. So I can break this up in such a way where I have my 0 to 1. And I got my function there. And then I have my 1 to 2, and then I can integrate my function. So one thing that this may show us is I've isolated the bad part, or if I get a limit that approaches two different values, then that means it is a discontinuous. Oh wait, we're not going over discontinuity. I was gonna say that it's a discontinuous function, but we're trying to see if it converges or diverges. Maybe that comes later. So, anyways, what I want to do here is state that this is the number in question that gets me in trouble. Therefore, I want to take the limit of it. So, go ahead, I'm going to do that. I'm going to take the limit as x approaches 1. So I now have the integral from 0 to 1 of 1 over x minus 1 squared dx. And then I'm going to add that. What's up?
0 to x, you mean?
0 to x, my bad. Fixable enough. And then from x to 2 of this guy right here. Well, take a moment. Find me the antiderivative of my 1 over x minus 1 squared, please.
You so.
Yeah.
You so.
Oh, wait, no.
And then we'll have it go. Yeah. Really? Okay. Negative.
Oops.
See what I mean?
I was going to select that and put it on the next page.
You can.
Okay.
Watch.
Is it squared? No.
What's your u sub going to be, by the way? X minus 1, so then you have a 1 over u squared, which is a u to the negative 2, which you can apply your anti-power rule there, no problem.
Thank you.
Ah, okay, doesn't want to do it. Okay.
That's all right. We'll just go to the next
Pardon
page.
me.
All right. So I feel like that's enough time to be able to take the antiderivative of that. What do we get? Slight.
Oh, wait.
I'm just dumping it on you guys because I don't feel like doing the
Say it.
You got it?
Yeah,
Oh.
he does. He just told.
Shouldn't it be negative 1 over u, right?
Yeah.
And that's from 0 to x, right? But we're taking the limit from there. So it's a limit as x approaches 1. Limit as x approaches 1 of the integral 0 to x from my bound 0 to x plus the limit, right?
Okay,
Plus
yeah,
the
yeah,
limit
yeah.
again
Yeah, for the other integral.
of the integral. Okay.
So just kind of to fast forward to the next page.
Yeah.
I will write the integral down. So it's going to be negative 1 over x minus 1. Okay. So here we go. I'm writing both limits. X approaches 1 from 0 to x. Was it x minus 1 or x plus 1?
Nope. We did the integral already, so it's no longer the integrand, it's the bounds.
For sure. I don't know, I'm kind of in the habit of writing that. I know that you would want me to write this.
Oh, okay.
Yeah, I just kind of in the habit of writing that. But anyways, he has a point. I probably should have just wrote that we're integrating over my bounds. It looks like I need to take another antiderivative. I definitely don't mean that. It's just a lazy notational thing. So I'm actually going to evaluate this at my bounds. I'm going to first plug in x, because that's my upper bound. So I got x plus 1. Oops. So I got x plus 1, and then I plug in 0. So I just have minus 1. So minus 1, we got plus 1. Okay, take the limit as x approaches 1. And then we're going to add that to the plugging in the bounds right here. So I plug in 2. So we got ourselves a negative 1/2. And then we have ourselves minus, so that becomes a plus 1 over x plus 1. Now, we have some nice some nice distribution properties with our limit right here. I can distribute the limit into just what we care about, which is the thing with the variable. I can take the limit of this and the limit of this, or I can combine them together, whichever one. As in, I can take the limit of this guy and the limit of this guy, or I could take the limit of when I add these things together. Wait a second. When I add these things together, we're good, right? Because we have a positive.
Top minus the bottom because there was a negative. It's minus 1 over x plus 1, right? But he just jumped straight to the plus because it's top minus the bottom, and the bottom's going to be the x, right? Top minus the bottom.
No, I'm talking about the u sub, because it was x minus 1.
Yeah. Is it x minus 1 or x
It was
plus
x
1?
minus 1.
Is it x minus 1?
It might be x minus 1. I might just wrote the wrong number. That's okay though. We still have the same denominator. We still have the same denominator. It's just we notice that we have inverse numerators. So we have additive inverses in our numerators. This is a negative 1. This is a positive 1. Therefore, they go away, right?
Right.
Yeah. Okay. So we have opposite things. I overlooked that we could have just canceled these out, and I was alluding to let's take the limit of these things. However, life's good. This and that cancel out. 1 minus 1/2 gets us to what? Which means we are convergent or divergent?
Convergent.
Okay, so this means we are going to converge to this value. So this means this is a convergent instrument. Very nice. Should we like plot that function just to like take a look at it and analyze it all?
No, it's good.
No, it's good? Okay. More practice problems then. Using the comparison test for improper integrals.
I could save this one for Tuesday.
The
'Cause
limit,
this one has
oh,
a
hey,
couple
this
more
is
in.
like sandwiching things, yeah.
Yeah, but
It's been a minute for me, sorry.
no. I'm saying because a couple of people got to go.
Yeah, okay. So you just want to say this?
Yeah.
Should we, should I walk around and help them through any problems?
No,
or the
it's
next
not. It's not a
problem?
whole class. This is just coming in for the notes.
Oh.
You guys want to stay and actually work, you can. But other than that, so yeah, a couple people got to go to work, a couple people got to go home. So that's thank you guys. So don't forget, every Friday we're gonna be doing this. I know, but listen, you guys be happy when you don't have to take, the Calc 2 in college. When you get that BC credit and you get the, no, it's not if, it's when. Okay.
Yeah, next year I'll get it.
All right, you guys. Thank you, Coach Grill.
putting up with that. That was kind of
Okay, don't forget, like, share, and subscribe. Watch. Hey, coach. Watch. Right here.